So let's start by thinking of how to deal with lots of types of the angles and coordinates on the unit circle. There are 8 total angle measurements that we're going to think about, and these are useful for evaluating coordinates of angle rotations on the coordinate plane. So let's assume that there is a unit circle with a radius of 1 on the coordinate plane like this. So there is a circle with a radius of 1. So there is firstly x-axis and there is an y-axis which result in the vertical axis. And on that there is a unit circle right over here. And obviously the midpoint will be the origin, what we call as 0, 0. And enable us to think about what is the definition for the unit circle. And before we think about the definition for the unit circle is a new concept where we apply to think about the new trig functions. So for a unit circle, we can think about the word from the unit, and unit states for the 1. And the unit circle's definition is it is a circle with the radius, and the radius again is the half of the total diameter of 1. So if the radius of the circle is 1, and we call that as the unit circle on the coordinate plane, that means, for example, any kind of lengths that are radius, for example, from 0 to the point right over here, it must be 1. And also from the y-axis intersections with the circle and to the origin, it should also be 1, and any kind of lengths where we approach from 0 to the end of the circumference of the circle, for example like this one, will also become 1. And this is the basic statements that the unit circle gave us. And this is the basic unit circle, and we need to think about how to set up this unit circle in terms of the angle rotations and the measurements. So there are a total of 4 values on the unit circle that is notated right now. Firstly, we got 0, pi over 2, pi, as well as 3 pi over 2. And we need to think about what are these values for. And these are the values of the angle rotations. So firstly, let's say the angle is 0. Then we will notate it as the 0. And we will talk about why it is noted as 2 pi after we finish a 1 period on the unit circle. Let's say from that starting line, which is the positive x-axis from the origin, then let's say we rotate it 90 degrees. And that means we'll reach to a positive y-axis right over here. And in order to think about the 90 degrees, in terms of trig functions, we always need to convert it in terms of the radians, which is a basic way to express the angles in terms of real numbers. So 90 degrees in terms of radian is pi over 2. And radian is basic and useful, as well as the most fundamental stuff that we usually use in terms of trigonometric functions. And if we cannot understand or if not familiar with it, you need to go back to my previous video about the radians and its properties, as well as how to convert it from degrees. So let's say from 90 degrees we went 90 degrees even more. 90 degrees plus 90 degrees will be totally 180 degrees. And from 180 degrees, it will be pi radians. And pi radian states for 180 degrees in terms of degrees. And let's say from that 180 degrees, we traveled the angle 90 degrees more. 90 degrees plus 180 degrees is going to be 270 degrees. And 270 degrees, after we rotate from the origin, it will stay on the y-axis, but the negative y-axis. And we notate it as 3 pi over 2 radians, which is equal to 270 degrees in terms of degrees. And from there, if we rotate 90 degrees even more, we go to 360 degrees. And 360 degrees, it is same thing with saying 0. But 360 degrees in terms of radian is 2 pi radian, where we finish our cycle or the period on our unit circle. And this is how we set up the basics for our unit circle. And we need to think about why do we need to use the unit circle. And there are two traditional approaches to defining trigonometric function. So firstly, the first way to think about the trigonometry is to use our right triangle. And again, the right triangle is a triangle with the right angle, which is 90 degrees from one of the angle measurements. And if you want to use the right triangle, we need to use the ratios or the proportions of the angles as well as size to solve for the values of the trig functions. However, there were a problem with it, where I talked about in a previous video about the comparison about the right triangle as well as the unit circle, where we cannot deal with the obtuse angle, and right triangle is only optimized for solving the acute angle. So the second way, or the second thing that we applied for measuring the obtuse angle, is what we call a unit circle. And for a unit circle, it is a circle with the radius of 1, where we can deal with acute right angles as well as the obtuse angle that can make our right triangle as a true statement on our unit circle. And this is the reason why we use our unit circle, and for more detail, you need to go to my previous video about the comparison as well as the difference between right triangle and the unit circle. And 360 degrees, 0 degrees from 360 degrees, is the end for our period on our unit circle, and this is how we set up our unit circle. But this is not the subject that we are interested in our unit circle. The thing that we are interested in are the coordinates that we're coloring right now, which are the intersections between the circle, the circumference, as well as the axis of x, positive x, negative x, and positive y, as well as the negative y axis. So we need to think about what will that coordinate be using our property where the unit circle. Whenever we're dealing with the unit circle, which is the circle with a radius of 1, we always need to remember that the radius, which is half of the diameter of this circle, should always be equal to 1. So when it starts off to 0 for the angle measurement, which is the positive x-axis, where the angle measurement is 2 pi radians, another way to say it is 306 degrees. Then the coordinate, which is foreign with the x, y, is going to be 1, 0. Since we know that the coordinate for the intersection of circumference of the circle and axis is on the positive x-axis. And if it is a positive x-axis, the radius of the circle should always be 1. So the basics for the coordinate is going to be 1, 0 for this angle measurement, where the angle is rotated 0 degrees. And after it rotates pi by 2 radians, another way to say 90 degrees, is the intersections with the circumference of the circle and the axis is on the positive y-axis, which means the coordinate is going to be 0, 1 with the same concept that we applied for the positive x-axis. And after we rotate 180 degrees, which is going to be pi radians in terms of the radians for expressing degrees, then the coordinate for this lies on the negative x-axis, so it will be negative 1, 0, where the x is negative 1 and the y value will be 0. And after we rotate the 90 degrees more from 180 degrees and reach 270 degrees, then the coordinate will be 0, negative 1, since we knew that the coordinate lies on the negative y-axis instead of positive. So this is how we set up basics for the unit circle, including the angle rotations and the coordinates of its terminal sides, which are going to be the axis. Now let's think about the random angle rotated from the string line, which is positive x-axis, and beside initial line and terminal line. From the origin, which is 0, 0, all the way to the circumference of the circle, for example, like that, which is going to be the terminal line for the angle measurement, and from 0 to the point here, which has the coordinate of 1, 0, we call it as the initial line or starting line. Then, for a terminal line, it will contain one coordinate that will express the locations for our angle measurements. And let's say the angle beside the terminal and the initial line is theta. And for the theta rotated from the starting line, which is positive x-axis. So we'll note it as the theta, and theta is a very definition of radian measures. Theta rotated counterclockwise directions from the origin and the x-axis. And if it rotates counterclockwise direction, where we assume it as a positive angle movement, we can notate the coordinate for the terminal line right over here in terms of x, y, which is going to be any coordinate on our coordinate plane. But in this case, it is on the first quadrant where x and y are both positive. And using this information where it is x, y, we can set up our basic right triangle to think about its coordinates. If we put a little segment with the right angle that shows that it's a right triangle, then the x value from the origin all the way to the point where it has an ending segment is where we call the x coordinate. And from this point and all the way down to the x-axis, we call it as the y value. And obviously this is a right triangle, which means the side that is opposite with our right angle is the longest side in our right triangle, where we call it as the hypotenuse, for the hypotenuse of our right triangle. So for the hypotenuse, it is going to be the longest side in our right triangle, as well as the opposite side of our right angle that shows that it is a 90 degrees angle. And using this basic trick setup, we can think about the new definition of our trigonometric functions. We already know that the adjacent side of the data is going to be the x value, since we know that is an x coordinate. The side that is opposite with our data is where we call the y value, because it's a y coordinate. And lastly, that the longest side in our right triangle is going to be hypotenuse. From here, we can make a new setup for our three trig functions, which are the cosine theta, sine theta, as well as the tangent theta. But we won't have to think about the tangent theta, because cosine and the sine are the only values that we are going to talk about right now. And if you want to know what the tangent theta is, we'll talk about it later. But firstly, for the cosine theta, how can we think about its value in our right triangle? Well, we can use the initial line for the cosine theta using our c, which is going to be initial line for a cosine theta. It always starts up from the origin beside the angle, our central angle. In this case, it's going to be theta. So it always starts from hypotenuse, and it will go all the way down, which is an adjacent side for our angle theta. And we use the c for the initial line for cosine theta for evaluating the cosine value. And wherever we start first and wherever we start last, whenever we start first, the side is going to be in denominator, and the side that we finish with is on the numerator. So that means the cosine theta, we started off the hypotenuse, so we will think about what the hypotenuse is. So it will be hypotenuse in denominator and the x on the numerator. But we need to remember that what is the hypotenuse on our unit circle right now? The hypotenuse of our unit circle is same thing with saying that it is the radius of our unit circle. And we always need to remember that the definition of our unit circle, where the radius of our unit circle should always be equivalent to 1. That means the radius, the hypotenuse of our circle, should always be equal to 1. So x over hypotenuse, where the hypotenuse of our right triangle can be simplified as the positive 1. This will be same thing as x over 1, which eventually is going to be x value. Which means in terms of the cosine theta on the unit circle, and this should always be on the unit circle because the radius, which is the hypotenuse of our right triangle, will simply be equal to 1. In our unit circle, the cosine theta will be the x. Another way to say it is the x coordinate in terms of the coordinate. Now let's think about what will the sine theta's value is going to be. And we can also use our initial line for sine theta as the s, as we have talked about. And if you don't remember this, you need to go back to my previous video where I talk about how to solve for the cosine, sine, as well as tangent using the basic initial line for each letters. For sine, it also starts off the hypotenuse and it will go all the way down to the y value, which is the opposite side of our data. And again, whatever we're starting from, the side will be in the denominator. We start from hypotenuse, so hypotenuse will be the denominator, and in the numerator it will be the ending line, which is going to be y value. So y over hypotenuse, but we always need to remember that only on the unit circle the hypotenuse is equivalent with the radius of our circle, which is going to be equal to 1. So the hypotenuse will be simplified as 1, which is going to be y over 1, and we get simply y value. So that means on the unit circle, only on the unit circle, the sine theta value is going to be the y. Another way to say it is the y coordinate in terms of coordinate of a point on the terminal line of our right triangle. So we got a new information, which is the new setup and the definition for our trig values. And for trig values, which are cosine and sine on our unit circle. So on our unit circle, and we always need to remember that the unit circle's definition is a circle with the radius of 1. And this is the reason why we apply unit circle to define the cosine and sine easier. The cosine theta was the x value again, or x coordinate for our unit circle. The sine theta is going to be our y coordinate for our unit circle. And now it's time to think about what is the tangent theta on our unit circle. Now we need to remember that the tangent theta's definition was always the sine theta over the cosine theta. And again, if you use our initial line for a tangent, which is going to be t, just like sine and cosine, unlike the sine and cosine, it starts from the adjacent side for our angle, and it goes all the way up to the opposite side for our data. And again, the tangent data, we can define it as the x in the denominator and the y in the numerator, according to what we have learned right here. And now we need to know what the y over x value states for. The y over x, we usually listen or see this term from the values or the function that contains slope, because y over x states for the change in y over a change in x, which are a difference between coordinates, and it's going to be the slope on our unit circle of our coordinate. So tangent theta can be simplified as y over x, and we need to remember that the y over x states for the slope of our unit circle and the coordinate. So y over x can be simplified as the slope of our coordinate or the unit circle in terms of sine as well as cosine values. And we might see what the tangent is more like after we solve the questions. But again, the cosine theta is x, sine theta is y, and tangent theta is slope on our unit circle because of our property where the unit circle's radius, in this case the hypotenuse of our right triangle, is going to be 1. So we define this, so let's erase all of the terms that we just used for spaces and begin with the another crucial informations that we're going to use that will help us evaluate other trig functions. So that means for the x, y, where the cosine theta is our x coordinate and the y value is our sine theta, we can convert the coordinate in terms of cosine and sine, where the x is cosine theta and our y value is our sine theta. So our cosine theta is going to be our positive x value, and the sine theta will be our positive y value for this coordinate. And this is all about the theta, which is an angle in terms of radians that rotate counterclockwise directions. And it contains the value of the x and y, and let's compare this with the angle negative theta, since we know that we rotated counterclockwise and assumed it as the positive angle. And what if we rotated the exactly same amount of the measured data to the clockwise directions? And we obviously know that if we rotate clockwise directions, the exactly amount of data will be same, but we need to remember that for this angle theta, it rotated clockwise directions, and if the angle rotates clockwise direction, we always need to assume it as the negative angle. So instead of theta, it will be the negative theta. But we need to think about properties comparing with the positive theta. If you make a right triangle, in order to think about the coordinates for the x and y value, we can naturally come to realize that the x value is common as the x. But only thing that are different is for the positive theta, it had a positive y value, but for a negative theta, it will have a negative y value as its y value. So we can think about what is the x and y value. The y value is negative y, x is positive x. So for a negative theta where we rotated clockwise directions from the origin, now we can think about the coordinate for this point that I'm notating right now. Well, we already know that we can notate it in terms of x and y as x and negative y, where the x value is exactly equivalent with the cosine theta and y value is exactly equivalent with sine theta. But we need to remember that this is a negative y value, since we know that the y value is negative from the negative theta. So we can convert x and y in terms of cosine and sine, where the positive x will be the cosine theta and the negative y will be the negative sine theta. So cosine theta will be our new x value, negative sine theta will be our negative y value, since we knew that it is a coordinate for our rotated angle in terms of radian, negative theta. But we can clearly observe that for this point where it contains cosine theta and sine theta as a positive x and a positive y, its coordinate, if we think about it as the first coordinate, it is x-axis symmetrical about the x-axis symmetrical with this point right over here where I'm going to notate as the number 2 coordinate. Now we can think about the new information. If the two coordinates are x-axis symmetrical, then from the original coordinate, which is cosine theta, sine theta, it will be converted as exactly equivalent thing as cosine theta, sine theta, except the y value will be opposite. In this case, it will be negative sine theta. So if we notate it, if the two coordinates are the x-axis symmetrical, then the original point, so usually the first one and the second one, was the x-axis symmetrical. Now let's think about what was the first coordinate. What was the first point's coordinate? Well, we can obviously see that it's cosine theta comma sine theta, where cosine theta is our positive x and sine theta is our positive y. Then it will be converted as a second point's coordinate, which is the x-axis symmetrical about with the first coordinate, and its coordinate is going to be cosine theta comma negative sine theta. It will be cosine theta comma negative sine theta, and we can realize that if the two coordinates are the x-axis symmetrical, then from the original coordinate, in this case it was cosine theta, where it was positive x and the sine theta was our positive y, then it will be converted as the cosine theta comma negative sine theta with the same x and with the same y, except the y value is our negative. So we can realize that if the two coordinates are x-axis symmetrical, only thing that are different is the y value's coordinate. And this was the first expression or information that we earned from this coordinate, and the angle measurements data as well as the negative data. Let's think about the second type of rotations of our angle. And we need to assume that every single angle's rotation to the central angle is going to be theta. And that means in this case, the angle theta is our central angle for this segment that we just used. That means this is also exactly equivalent with any single theta that we looked at right now. And we can obviously remember that there is obviously a coordinate where we can express our locations of our angle. Now when you think about, we need to think about what is our total angle measurements that the angle rotated. Well, we already know that the 90 degrees is from origin, you go 90 degrees, but from there, you subtracted the amount of theta. So that means from the 90 degrees total, when you subtract the amount of theta, then you will get from this ray until it reaches the positive x-axis, it will be its angle measurements, and we can express it as 90 degrees minus theta, and 90 degrees in terms of radian is pi over 2 minus theta amount. And this is how many angles that we rotated from the origin. And now we can see that we rotated pi over 2 minus theta amount from the positive x-axis. And now when you think about the property for this coordinate, well, we need to remember that this angle, this coordinate, and the first one, so let's say this coordinate is the third coordinate, first coordinate and third coordinate has a special properties or similarities between them. They're both theta apart from the axis. So now we can make a new concept where they're symmetrical about a linear functions. And that linear function is what we call y is equal to x line. So this is the line y is equal to x, and y is equal to x has a special property where we switch the x and y's positions. So we're going to talk about it in a few next videos. But what will the exact value that the y is equal to x does to our coordinates to think about how to solve for the angle measurements easily with these properties. But now let's just remember that if it's y is equal to x symmetrical, then the x and y's positions will get switched. So our goal is to write the coordinate here, which is the intersection between the circumference of our circle and our terminal line of the 2 pi over q minus theta. But there are totally two ways to write this coordinate. And whenever we're writing our coordinate, we always need to make a right triangle to think about its coordinate. The first way to make a right triangle is to make a triangle in this way. And another way to make a triangle is to make a triangle in this way. Now we can think about this value. Now we can simply realize that these two triangles are congruent. The lengths here should also be exactly lengths with the x. The lengths of the y value should be exactly same lengths because this is a rectangle. So there are two ways to do it to make a triangle. But anyway, whatever the triangle we pick, the coordinate will be exactly equivalent. However, when we're trying to deal with the symmetrical values of our angular rotations, in this case pi over 2 minus theta, and the data, we always need to rate this in terms of the triangle that I just erased, and we are going to use this triangle whenever we're thinking about the symmetrical coordinates. And the reason is because this is more effective when we're talking about the symmetrical values, where we can solve for that coordinate easily, and this also affects the other coordinates. And in the next video, I'll talk about more detail the difference between the first triangle and the second triangle. But in this case, we need to use the triangle that is on our first quadrant right now. So anyway, the third one and the first quadrant are the y is equal to x symmetrical. That means the y value that I'm circling with the white yellow color, and the x value that I'm going to write as the yellow color also will get switched and it will be rotated. So that means the y value will now be on the x value, and the x value will now be on the y value for the angular rotations of pi over 2 minus theta. So now we can see that now we have y value as the x and x value as y, and that is the main property of y is equal to x. And using our property of y is equal to x on our equation, we can easily solve for a coordinate without even thinking about it. So now we can think about the coordinate for this point. Now we can say that the positions of our cosine and sine theta has changed. So in the x positions, the sine theta will go there, and for the y positions, the cosine theta will go there. The x and the y positions are exactly same, so this will be x position and the y position are same, but the difference is the value that goes inside the x position and the y position. Inside the x position now, the sine theta will be there, and for the y position now, the cosine theta will be inside there. And this is what the y is equal to x affects our coordinates. So now we can think about new informations, where if the two coordinates are the y is equal to x, the linear function is symmetrical, and the main example was the number 1 coordinate and the number 3 coordinate. Then what happens is from the number 1 coordinate, let's say the number 1 coordinate was our standard coordinate, cosine theta comma sine theta. Then it will be converted into the number 3 coordinate, and for number 3 coordinate, it is going to be sine theta comma the cosine theta. And if we review what we have done, if the two coordinates are y is equal to x symmetrical, then from the original x position it was the cosine theta, and from the original y position it was sine theta. But as it is symmetrical to y is equal to x, the x and the y positions won't change, except the value that goes inside the x position and the value that goes inside the y position will get switched after the two coordinates are y is equal to x symmetrical. And this is the basic informations for our coordinate when they're y is equal to x symmetrical. And now let's think about the point on which is the first angle on our second quadrant. So let's say there is an angle here, and that means we need to make a straight line from there all the way to the origin where it is 0, 0. Then we, as I mentioned, the central angle should always be equal to theta, which is exactly the same theta that we all just looked at right now. And we can remember that what is the total angle measurements? We already know that the 90 degrees is what we call the pi over 2. But from there, we went data amount even more. So the total angle measurements that I'm notating right now all the way to the positive x-axis, the angle measurement will be 90 degrees, which is pi over 2 radians, plus theta. And this means from the 90 degrees, we added the amount of data, and it creates our new angle measurement, pi over 2 plus theta. And let's change the color not to be confused with the pi over 2 minus theta angle. So here is pi over 2 plus theta, and we need to think about its coordinate because that is the most interesting thing that people look at on the unit circle. And the next is going to be the angle measurement or the rotations on our unit circle. And in order to think about the coordinate, we always need to make a right triangle. And again, there were two types of ways to measure it. First way is to make a triangle like that, and the second way to make a triangle like that. But as I mentioned, in order to think about the symmetrical, we need to make a line that I'm notating just like right now, and to satisfy the definition of symmetrical, and we'll talk about it more detail in the next video. And we need to compare this coordinate with the point here where the coordinate is sine theta, which is our new x, cosine theta, which is our new y value. And we can see that this triangle, and let's say that this has the fourth coordinate, the triangle that has the first coordinate is exactly congruent with the triangle that has the third coordinate, except it is the y-axis symmetrical, where the x value is still y, just like the value that is y-axis symmetrical, but we already know that it is on the second quadrant, which means the x value should always be negative. But for the x value, they share exactly common and same as the x value. So that means the coordinate for this point is going to be the x positions as the negative y. It has exactly x as the value of the number 3 coordinate, except it is the negative opposite coordinate. So it will be negative y, comma, the positive x, which is the y value. But we already know that in terms of the trig functions cosine and sine, we can convert it as the negative sine theta, comma, the cosine theta for this coordinate. And we can see that from the original sine theta, it has been converted to the negative sine theta. From the positive cosine theta, it has the exactly same y value. So from the positive x, it has switched to the negative x value, and from the positive cosine theta, it has the exactly same y value. And this point, negative x comma y, which is the number 4 coordinate, is y-axis symmetrical with our third coordinate. So we can have a new information if the two coordinates are y-axis symmetrical, and we need to not confused with the x-axis symmetrical. And the main example was the number 4 coordinate and the number 3 coordinate. So for number 3 and number 4, there's been a change in our coordinate. For number 3 coordinate, it has been changed by the y is equal to x property into sine theta, comma, cosine theta. So sine theta, comma, cosine theta will be our coordinate for number 3. But from there, it has been switched to the number 4 coordinate, as they are y-axis symmetrical, into negative sine theta, comma, the cosine theta. So now we can clearly see what is the difference between them. If the two coordinates are y-axis symmetrical, from the positive x, which was sine theta in this case, and the positive y, which was the cosine theta in this case, and it was the coordinate for number 3, then it will be switched into negative x and the same y coordinate. So we can have a conclusion where if the two coordinates are y-axis symmetrical, they will have exactly the same values, except the x coordinates are opposite symbol. So from x comma y, it will be switched to negative x comma y. And this is a property of y-axis symmetrical. So the third one and the fourth one was y-axis symmetrical, and this point total rotation was pi over 2 plus theta. Now let's think about the lost angle measurements on our second quadrant, where x is negative and y is positive. So the lost angle rotations for our angle measurements on our unit circle on the second quadrant is something that look like this, that is have an intersection with our unit circle circumference. So obviously the central angle is going to be data that is exactly the same with the any kinds of data that we all looked at from the beginning. And now we always want to solve for the coordinate for this, and I'm recalling this that before I finish this, I'm going to review about the angle pi over 2 minus theta and the theta, because it is the most important thing in this chapter. And if you think about the coordinate here, it's a little bit different with any kinds of angles that we looked at, including 4 and 3. And we might think that it will still be something about like sine theta comma cosine theta, but it is different. If we make a right triangle to solve for its coordinate, we can figure out that the x value here is from this coordinate and all the way to the origin. So this will be the x coordinate, and the y coordinate is from this point all the way down. But now we can see that this has a similarity with the first triangle. If you say that this is a fifth coordinate, the triangle with the fifth coordinate is exactly congruent with the first triangle. They have exactly same lengths of the height, and they have exactly same lengths of the base, except the x value is negative. So this value won't change as sine or cosine. This value will have its standard positions of cosine comma sine theta, and we need to think about what is the angle rotations for this before we think about any coordinate. And we already know that for the pi radian, it is this 180 degrees that I'm coloring right now. From 180 degrees, which is pi radians, you subtract the amount of data. That means what we get is from here all the way to the x positive axis. And this is how we solve for this measure. So if we erase the rest of them, then we get the angle measurement right over here. And is there any way that we can express this angle rotations? And there is, because from 180 degrees, which is pi radian, we just subtract the amount of data, which is going to be pi minus theta amount. So for that coordinate, it is going to be cosine theta comma sine theta, but we almost forgot that it has the negative value of the x, since we know that it is on the second quadrant. So we can say that our new x values positions is going to be negative cosine theta, it's the negative x. Sine theta is going to be our position of y. Negative cosine theta is now currently in the x. Sine theta is currently in the y value. And now if you look at this carefully, if you observe this coordinate and the first coordinate are what we call the y-axis symmetrical. So the first and the fifth are the y-axis symmetrical, and now from these coordinates we can review what was the property for y-axis. Now we can see that from the x comma y, only thing that is different is the sign or symbol for our x, which exactly satisfy our property of y-axis. And this was the coordinate when we rotate 180 degrees minus theta amount, which is pi minus theta in terms of radians. And this was the last coordinate or angle rotations or measurements on our second quadrant. And after the second quadrant, as we get to the third quadrant, every single angle measurements will be over pi. So let's think about the 1, 2, 3, 4, 5, 6 coordinate on our third quadrant of our unit circle. So the first angle measurement on our third quadrant, where the x and the y are both negative, will look something like that. And obviously the central angle of this will also be theta, which is exactly the same angle measurement of theta that we all just looked at from the beginning. And we are interested in what is this coordinate as well as the angle rotations. Firstly, let's think about the angle rotation first. And if you think about the angle rotations for this coordinate, we already know that 180 degrees is pi radians. But from there, we just added the amount of the theta. Then obviously it will be pi plus theta amount, which is 180 degrees plus theta. So from this 180 degrees, if you add the amount of theta, we'll get the angle measurement of this total. So let's actually notate that angle measurements. So from 180 degrees, if you add theta amount more, then you will get the amount of this angle. And we will call this angle as pi plus theta. And the reason why it's called pi plus theta is because from 180 degrees, you just added the amount of theta. So now you will get the pi plus theta, and all you have to do is solve for pi plus theta as coordinate, which is the most interesting part on our unit circle. So in order to solve for the any coordinate, we always need to make a right triangle. And again, for thinking about the symmetrical lines, we need to make the right triangle like that. And if you make a right triangle, that means if you make a right triangle, that means the x and the y should be notated. This is a right triangle. This one will be the new y value, but we need to remember that it's on the third quadrant. The property of third quadrant is that the y value is negative. And for the x value, it shares the common value as the negative x. So for this point here, we can notate it. We could notate it as the negative x, comma negative y, but we always need to convert it in terms of trigonometric values as sine and cosine for coordinates. So for that coordinate, negative x is going to be negative cosine theta, and negative y will be the negative sine theta. So this coordinate will be negative cosine theta, comma negative sine theta, where negative cosine theta is our new x value, but in this case it will be negative x, and negative sine theta will be our new negative y value. So in this case, for the coordinate of pi plus theta, where from 180 degrees we added pi plus theta, then the x coordinate will be negative cosine theta, and the y coordinate will be the negative sine theta. And this is how we solve for the coordinate of this value. And again, this was the example of the x-axis symmetrical between this coordinate set 5, and if we call this as a 6 coordinate, 6. So for x-axis symmetrical, there were one more example as 5 and the 6 one, where we can actually prove the property of x-axis symmetrical again. And we need to remember that if it's x-axis symmetrical, the x value should always be exactly equivalent, except the y value will be the opposite. Now we can actually prove it. From the first one, it was negative x and the positive y. It has exactly the same value as the negative x, except from the positive y, it will have its opposite value as the negative y. And this is how we solve for the angle measurements coordinate. Now let's think about the last coordinate on the third quadrant. And the last coordinate on our third quadrant looks something like this. And obviously the coordinate, the main angle, central angle between the terminal line and the axis is going to be theta. And again, the data has exactly the same amount of value as every angle measurement that we all just looked at. And we are interested in what is the angle rotations. So we can say that it is the angle rotations where we rotated from the origin. And what if we rotated 270 degrees? If we rotate 270 degrees, then we will reach 3 pi over 2 radians. But it didn't reach yet. From 270 degrees, we subtracted the amount of data. That means the total amount of the angle rotation is from this 180 degrees. So from this 180 degrees, which shows the pi radians that it rotates from the origin, and it rotates 90 degrees, it will be 270 degrees. So in order to solve for the angle measurement, from the pi over 2, 3 pi over 2, you need to subtract amount of data, such as this, and you will get the total angle measurement that I just colored with the green color after we subtract the amount of data. So this one will be 270 degrees, and 270 degrees in terms of radians, 3 pi over 2 radians, minus the amount of data. And this is how we solve for the angle measurement. And again, if you want to review how we did it, if we go the 90 degrees more from 180 degrees, it is 3 pi over 2 to 70 degrees. However, we need to subtract the amount of data, and that is going to give us the total angle measurement. So 3 pi over 2 minus data, 270 degrees minus data, will be the angle measurement for these rotations. Now, after we solved for the angle rotations, we're interested in this coordinate. And the coordinate here, we can solve this coordinate in 2 different big ways. The first way to solve it is using our property of y is equal to x line. We already know that this line is y is equal to x line that has a property where if they're symmetrical together, the x and the y value will get switched. So if you make a right triangle to think about the coordinate, from here we always need to make a right triangle with an acute angle and the right angle to think about the symmetrical properties. That means this will have a right angle and become a right triangle. And then we can realize that what is this point symmetrical to? If we call this point as the 7th point, then according to this line y is equal to x, obviously the 7th and the 6th are symmetrical together. And again, we have one more examples. The 6th and the 7th angle rotations and the coordinate are symmetrical about y is equal to x. That has a special property where the x and the y value will get switched. So that means from the original 6th coordinate, which was the negative cosine theta, negative sine theta, the coordinate will get switched into negative sine theta, negative cosine theta. And what happened is, using our property of y is equal to x, where from cosine theta and sine theta, it will get switched as sine theta and cosine theta with the same symbol of x and y value. So if it was originally cosine theta, negative cosine theta, then it will be switched as the negative sine theta. If it was originally negative sine theta as a y value, then the y value will get switched as the negative cosine theta. But however, the negative sine theta will still be x value, but negative x, but negative cosine theta will be our negative y value. So we need to remember that the x and y positions won't change, except the value that goes inside those positions will change. And the 6th and the 7th was the example for the y is equal to x symmetrical. But however, we can solve for this coordinate in terms of origin symmetrical. And now if you think about the word origin symmetrical, then we can think about the 180 degrees beside those terminal lines. So we can realize that even though it doesn't look like, from this point, which has the sine theta, comma, the cosine theta, and this point, which is negative sine theta, comma, negative cosine theta, the x value and the y value will get switched. Not switched, but the angle that is being formed between them should always be pi radian, which is 180 degrees. Then if we realize that the angle measurement between the two terminal lines are 180 degrees, pi radians, then they are origin symmetrical. And we need to think about what will the origin symmetrical if the two coordinates are origin symmetrical together. And the main example is the number 3 and number 7th, where the number 3 and number 7's terminal line, the coordinates are origin symmetrical. Then from the number 3 coordinate, which was sine theta, comma, cosine theta, it will get switched into number 7th coordinate, and the number 7th coordinate was negative sine theta, comma, negative cosine theta, which means if the two coordinates are origin symmetrical, then from the original x value, which in this case was sine theta, and the original y value, which was in this case cosine theta, they will have exactly opposite symbol as the negative sine theta and negative cosine theta in this case, and that's the property of origin symmetrical. And number 3 and number 7 coordinates were the main example that we could look at right now on the unit circle. So we could have solved this angular rotation's 3 power 2 minus theta's coordinate in terms of two ways, as the origin symmetrical and the y is equal to x symmetrical. And this was the last angle on our third quadrant. Now let's think about the last angle measurement, which is going to be the first angle measurement in our first quadrant. And from the origin, it will look something like this, with the same central angle, or the main angle that defines the trig function, as the positive theta. If it is same thing with positive theta, in order to think about its coordinate, from the point which is an intersection with the terminal line and the circumference of our circle, we always need to make a straight line to think about a right triangle. Since we made a right triangle, what we can do is we need to think about what is the rotations for this angle. And we can realize that from the 270 degrees, so 270 degrees is an angle that I'm coloring with the orange color, then from there we added the amount of theta. So the total amount of theta that we're going to new color it after we add the amount of theta, this coordinate, or this angle measure, is going to be 3 power 2, which means after we reach the 270 degrees in terms of degrees for expressing 3 power 2, and then we added the amount of theta. So 3 power 2 theta plus theta, which is same thing with saying 270 degrees plus theta, is going to be the angle measure for this last angle. And this is how we solve for the angle measurement. And the next thing that we are interested in is the coordinate for this point. And now we can realize that if this is the y value, then it has the exactly same y value as the y value of the point where we rotate 3 power 2 minus theta. And that means this one originally had the y value as negative y, and now we have the y value as the positive y. So if you have the positive y value, we can think about its coordinate in terms of y-axis symmetrical with the 7th point. If we call this point as the 8th point, then 7 and the 8th are the main example for y-axis symmetrical. So the 7th and the 8th are the main example for the y-axis symmetrical. And again, for the y-axis symmetrical, if you rewrite the definition with the same x and the y value, the only thing that are different, not y is equal to x, y-axis from the same x and y value, the only thing that are different will be the negative x, which means the different x coordinate, and the y same symbol value. So if these 2 points are the y-axis symmetrical, that means the coordinate here will be exactly equivalent with this point as negative sine theta, comma negative cosine theta, except these are y-axis symmetrical, which means the y value should be exactly equivalent as negative cosine theta, but the x value should have the opposite value. So for negative sine theta, it must have the positive sine theta. So this coordinate is going to be the sine theta comma negative cosine theta, where the sine theta is our new position that goes inside our positive x value, and negative cosine theta is our value that goes inside our new negative y position. And we solve this coordinate through the y-axis symmetrical property. And we solve for every single angle measurements or angle rotations from 0. So if we review what we did here on the unit circle, so firstly we could there were a lot of types of the angles in our unit circle, and we could solve it through the properties of the x-axis symmetrical. Y is equal to x symmetrical, which was the most important property, y-axis symmetrical, as well as the origin symmetrical. And the reason why we think about these properties is to think about the obtuse angles on our unit circle faster and easier for that coordinate. So, and the second thing to remember is that for on the unit circle, we define that the cosine theta is our new x value, sine theta is our new y value, as well as the tangent theta, which is going to be the slope on the unit circle about the coordinate. And the third thing to remember is that the unit circle's definition is that it's a circle with a radius of 1, and there were 2 traditional ways to approach the trig functions, whether we use the right triangle or the unit circle. But for a right triangle, we need to use the ratios of the angles and the sides, which has a little bit of limitations because we can only measure the angle in terms of the acute angle. But for a unit circle, we can measure acute right as well as the obtuse angle. And the last thing to remember is for the angles measurement that we just looked at, for example, the point coordinate here, we got a sine theta comma cosine theta because of the property of y is equal to x. So our main goal is to read the coordinate here, and there are 2 ways to read it. Either you can make a right triangle in this way, or the right triangle that we just looked at. Anyway, that 2 triangles are congruent together, where this side is congruent with this side, and this side is congruent with this side right over here. And no matter what the triangle we use to read this coordinate, the coordinate will be exactly equivalent because they share a common values. However, if you think about the y is equal to x symmetrical properties and not only other symmetrical problems, and we are thinking about what is the coordinate or the triangle that is symmetrical with the first one right over here. And we can't just say that this triangle is symmetrical with this triangle according to y is equal to x. And it's not wrong, but when we are thinking about the symmetrical stuff or properties, we always prefer to use the coordinate or the triangle that I'm coloring right now about the y is equal to x symmetrical with this one, for example, to solve for the coordinate as well as the angle rotation easier and faster. And in the next video, we're going to talk about what is the difference between this triangle and the reason why we use this triangle when we're dealing with the triangle angle measurement and the properties of symmetrical in the next video. And when we're thinking about the radians or degrees, where the radian is the most useful and the most fundamental subject that we use for notating the angle in terms of real number. If you don't understand it, you need to go back to my previous video about the understanding of the radians, where we can apply to the trigonometric functions. And in conclusion, this might be unclear when we're first thinking about dealing with the types of the angles on the unit circle. But in the next video, we're going to solve for the actual examples where we can actually apply all the properties, including y is equal to x properties, and how it will be applied to solve the questions. And from there, we can derive some formulas where it will help us solve for the questions about the types of the angles on our unit circle.